Well, I'm going to talk about some recent work that we just started. It settles on the field of uniform spaces, but then the results, the first result that we have obtained is on the subfield of topological models. So this talk is divided in two sections. The first one is just a review on uniform spaces. Like everything here is very well known. You can just find it in any textbook. But I just want to give the insight of the importance of uniform spaces. Uniform spaces, they were conceived in order to define properly very well-known notions such as uniform continuity, Cauchy sequences or Cauchy nets, and completeness, and uniform convergence, you know. And then it gathers, for example, the uniform continuity that you can define on a metric space or on a topological model or stuff like that. It's important to mention that well, there is this notion of, well, we will focus on uniform convergence, okay? I will give an insight about uniform spaces in general, but we will focus on uniform convergence, the topology of uniform convergence, and it is worth mentioning that there exist the convergence topologies that you can define on general function spaces. Let's say x to the y, this is the set of all maps from a set I to a topological space X. And then there is the uniform convergence topologies, which are defined or constructed on function spaces where, again, I is a non-empty set, and X now is a uniform space, okay? So by means of several examples and a very simple result, we'll show you that it makes much more sense to consider the uniform convergence topologies for the main purpose of this work that we have just started, whose motivation I will give at the end of the talk, not at the beginning as usual. Okay, so I'm just going to go very quickly over section 1 because this is just all very well known. Well, this is the definition of uniformity. It's simply a filter in the power set. This is the power set of x times x, and it verifies the basic properties, you know, that reminds of metric spaces on topological groups and stuff. Well, this is a simple remark, just very simple notions, you know, symmetric entry edges, filter basis of the uniformity is called a base of entry edges. You know, you can restrict to a base of symmetric entry edges, and finally, you can define like the ball of center X, you know, but in the uniformity. Okay, so it's just a generalization. Well, examples in the metric spaces are examples of uniform spaces, and topological groups, so in particular topological rings, modules, topological vector spaces are uniform spaces also. Okay, well, the uniform topology is constructed similarly to the way you construct the metric topology or a linear topology, and well, the interior, you know, if you take the balls centered at x, then that's a base of neighborhoods of every x. So this is just basic stuff, very well known. Well, uniform continuity, our work is not related to a uniform continuity, but I will just remind you of this notion in uniform spaces. Now it makes sense between a function between uniform spaces is said to be uniformly continuous, provided that, well, you have this thing, no? So this generalizes uniform continuity in metric spaces and in topological vector spaces, for example. The same with completeness. You have the, well, since we don't have to have second countable or first countable topological spaces. So we have to work with filters, with pre-filters or shear filter bases, and also or with nets, because there's like a correspondence between nets and filter bases. So you just define the notion of Cauchy prefilter, and the most natural example is a Cauchy net. So a net in a uniform space is said to be Cauchy, provided that the induced filter base is a Cauchy prefilter. And it's very easy to prove that this is the classical notion of Cauchy net or sequence. It's a Cauchy, if and only for every entourage there exists lambda sub 0, or so that the Cauchy condition that we all know. And well, the classical lemma, if B is a convergent prefilter in the uniform topology induced by the uniformity, then B is a Cauchy prefilter. In particular, if you have a convergent net, then it's a Cauchy net, and the converse is just the definition of completeness, and uniform space is to be complete, right? That every Cauchy prefilter is convergent. This generalizes completeness in metric spaces, completeness in topological vector spaces, and stuff. And actually, well, it's very easy to prove that a uniform space is complete if and only every Cauchy net is convergent. Okay, so it's defined for prefilters, but it can be characterized through nets. And now uniform convergence, which is the tool that we are going to use later. Well, in a function space, x to the y, all maps from a set I to a uniform space X, you can define this kind of entourages, and then the set of all of these entourages is a uniformity base. So it induces, this is a filter base, and the generated filter is a uniformity on X to the Y. So you have, so every uniform space induces a uniformity here. Okay, and then the induced uniform topology, I mean the topological convergence in the sense of filter bases in the uniform topology here is what we call uniform convergence topologies, which in the case of, for example, topological modules, they are called uniform convergence linear topologies, because they're also linear topologies. But this is basically it's probably the insight is probably better if using nets. If you have a net of functions, this net convergence to another function in the topology induced by the uniformity, if and only if the convergence is uniform in every element of the subset G. Usually, this subset sometimes is the finite subsets, and then you obtain the pointwise convergence topology or the product topology, or sometimes is the bounded subsets or any other Bornology, or in general any other upward directed subset. Okay, in the power set of I. Well, and then, well, this is just standard definition. Some authors use this definition. You have a non-empty set and a subset of the power set of I upward directed. For the inclusion, obviously, then a uniform space, a subset of x to the y is called a function space if it is endowed with with the inherited convergence uniformity, okay, given by the subset calligraphic G, whose induced topology is finer than the pointwise convergence topology. Okay, so in order, this is sometimes asked for the coordinate functions to be continuous. Okay, that's basically. Actually, if you, like I said before, if you choose calligraphic G to be the finite subsets, then you obtain actually the pointwise convergence topology. Here. Well, some recent advances. Well, first, I'm just gonna provide like a simple remark. Well, I stated as a proposition there, but it could actually be a remark because the proposition is very simple. the convergence, if you have a topological space, X, okay, topological space, you can consider a function space. Let us take the set of all maps for a non-empty set I to X, and then you can induce this with a general convergence topology of this form. Okay, this is the general convergence topology. It is this is in general topological spaces, and it is related to the uniform convergence topology. It is related, but they are constructed similarly, but not exactly, because the uniform convergence topology is constructed by means of filter bases, and this is constructed by means of a sub-base for a topology. So these are these different notions, different concepts, but they are somehow similar. Actually, there is a relation between the entourages of the uniform convergence topology and these elements of the sub-base. And the classical example is the compact open topology. This is just an example. I didn't I didn't go deeper on this. It's just an example to show an example of convergence topologies. But the point is that depending of the subset G that you use here for the general convergence topology, you obtain decent topologies like the point-wise convergence topologies or the compact open topology, or you can obtain very weird topologies if you take G to be very, very big. So the thing is that, well, this is just a remark, if you take on a general topological space and on a non-empty set, if you take a subset G upward directed, a subset of the power set of I containing the finite subsets of I, then the general convergence topology is finer than the point-wise convergence topology and coarser than what some authors call the uniform convergence topology. So you have this situation, you have the general convergence topology is contained in the convergence topology provided by the whole power set, and then this contains the point-wise convergence topology. Okay, this is the point-wise convergence topology, which is actually the product topology of X to the Y. So what some authors call the uniform product topology? The uniform product topology, if you take a product of any family of topological spaces, the uniform product topology is just the topology generated by the base of products of any open subsets. Not only finite number of open sets and then the rest is just the whole space, so any open. So that's a very weird topology, because you can have if the underlying space X has very decent separation properties, then in the uniform product topology you can find, for example, sequences or nets which only are convergent if they are constant. For example, something like in the discrete topology. It's a topology with too many open sets. So then this is contained, you can easily see that this is contained in the, this is X to the Y, in the uniform product topology. Okay, where a base of open sets is just products of any open subsets of X. Okay, this is clearly a base. It generates a topology. It's called that. So the point is that the further that you approach this, the easier that you obtain weird topologies that don't really work in order to construct other stuff. And well, basically here it's natural to ask whether these two topologies are the same, and in general they are not the same, but it doesn't really matter. Like if you take this Bornology, then well, the whole power set, still this topology it contains usually less open sets than this one, but still contains too many open sets. Well, this is just it's a theorem, but it could actually be a remark. This is just a characterization of when these two topologies coincide. Okay, this is basically working with basis of topologies and stuff. This condition has to be verified. For any family of non-empty open subsets, there exists a finite number of non-empty open subsets of X in such a way that Xi is contained here. So this implies, in particular, that you cannot have an infinite number of disjoint open subsets. Okay, so these two topologies coincide if and only if X is a rare topological space. But still, even if they don't coincide, these two topologies are very strange. So usually, when working with general convergence topologies, you only work with the product topology, the pointwise convergence topology, or with the compact open topology. This is often used. So now in topological modules, for instance, it's not easy to find many compact subsets, or in topological vector spaces. So general convergence topologies are not really useful. So this means that we will stick to uniform convergence topologies. So now, what is the motivation of this whole thing that I have just been talking about? Well, the idea is to develop a theory. There is something now that is it's a very hot topic, which are the Hilbert C-star modules, which are essentially, it's just basically a module over a C-star algebra. Okay, so module, A is usually a left module, and A is a C-star algebra. Okay, and you can develop. I don't work on this, but I'm familiar with this kind of topological modules because, well, you can actually develop a semi-Fredholm theory and stuff here. Okay. So now the next step, or one of a possible next step, is to develop a differential geometry theory on based on topological modules or topological vector spaces. Okay, and the idea is to consider topological spaces or topological manifolds, but which they are not locally homeomorphic to Rn. But they are locally homeomorphic to for example, to a Hilbert space, a complex Hilbert space, or to a real Hilbert space, or to a Banach space, or to a topological vector space, or more generally to a topological mode. Okay, so this is like the infinite dimensional version of a manifold. Okay, so now so then the notion in differential geometry, the notion of directional rate of change, directional derivative, differential is very important. So this is the point now. Well, this is also a very well-known notion in this talk, that there are more review results than original results. There is a motivating result. The notion of derivation is very well known, okay, and it's just an additive operator which satisfies the product rule, okay, and is used. Derivations are used in algebra, even in differential geometry, by means of the classical bracket. So two representative, there are many more, but two representative examples are the inner derivation and the classical Lie bracket. Well, this is very simplified. It's a little, there are many missing details there, but the idea is basically that the Lie bracket, if you fix one coordinate, then induces a derivation. Well, so now, there are other examples of derivations given by the derivative operator. And this is what we are going to consider now in Hausdorff topological models. Okay, we now ask them to be Hausdorff because of the unicity of the uniqueness of the limit. Okay, well, this is just another standard definition. I restricted this definition to functions defined on the whole module, but it can be redefined for functions defined on an open subset. Okay, it's not hard to redo the same thing, but for the slides, it's much easier. You know. Well, this is the typical rate of change. You have to multiply by the left from the left because we are always work with left modules, and the topological ring needs to be practical. Practical means there are many practical topological rings. A topological ring is practical. That means that that 0 belongs to the closure of the invertibles. Okay, you can approach the invertibles by, you can approach 0 by invertibles, by a net of invertibles. Well, these are invertibles. Actually, because in order to define the derivative, you know the invertibles have to approach 0, otherwise it's impossible. Or you would need a different definition of derivative. Well, the differential, this notion generalizes the classical Gateau derivative in a Banach space, which is also very well known. It's just, well, a function is differentiable, provided that this function, well, the directional derivative exists and the function is linear and continuous. Okay. Some authors, they remove the continuous condition. Well, for now I left it. And then the uniform differential, this is why we needed a clear understanding of the uniform convergence in uniform spaces. This generalizes the Frechet differentiability. Okay, this is just a function is said to be uniformly differentiable if it is differentiable, and this convergence, these functions are functions of in the space, in the function space n to the m. So now, so you need to endow this with a linear topology and with a uniform convergence linear topology, and we will endow it with the topology generated by bounded subsets, by the Bornology of bounded subsets of M. Okay. So if this convergence is, so if this is a limit, a topological limit in the topology of uniform convergence on bounded subsets, then we say that the F is uniformly differentiable. If you wanna break it down into neighborhoods or entourages, or this would be something like for every 0 neighborhood in N, and for every bounded subset of M, there exists another 0 neighborhood in the ring, the topological ring, which only depends on the 0 neighborhood in N and on the bounded subset. Okay, in such a way that these are functions of little. So Fm r minus dl. This is the directional derivative and the directional rate of change. This belongs to U for all L in the bounded subset. So it's uniform. So it's uniform convergence on bounded subsets. Okay. So and now this is, I think I went too fast. Oh no. Okay. Yeah, but this is just the last. So by means of the differentiability and uniform differentiability, we were able to prove the chain rule in topological models. As far as I know, I still have to check much more literature because there's a lot of literature and not so famous literature, but as far as I know, the chain rule, the farthest thing that has been proved is in Banach spaces. So here we accomplished the chain rule with differentiability of G and uniform differentiability of F at G of N. Why is it important, the chain rule? Because if you have a topological space, which is locally homeomorphic. It's locally homeomorphic to a topological model, okay? And so the charts, okay, so function from, well, doesn't matter because it's a homeomorphism, but let's say here, well, let me just write the inverse. So where the charts intersect, in order for the charts to be compatible, you need the chain rule. That's just basically. So you cannot develop a general theory if you don't have. You need a derivative between the underlying linear structure, the underlying local linear structure, and then you need the chain rulers. Okay. This is the end of the talk. Thank you very much.
So,